Good afternoon, everyone. Welcome to week 3 problem solving session for the course on regression analysis. I am Shreya, one of the TAs for this course, and today we'll be discussing problems related to week 3 lectures. So, let's get started. Alright, so just to touch up briefly, I'll discuss what has already been discussed during week 3 lectures. So during week 3 we have seen these things. So in the previous 2 weeks we have seen how to fit a linear regression, and also we had some introduction into how to fit a multiple linear regression. Okay, so this week we have discussed in details how to fit a multiple linear regression and how to test for significance of the regression model. What I mean to say is that if at all this model makes sense. So testing of significance of regression model means whether the predictors that I am using are actually helpful in predicting the outcome of interest. So that is assessed by testing significance of the regression model. And apart from that, we also learnt how to test for significance of individual regression coefficients. So for a simple linear regression we had this thing where we tested for significance of only one beta. Here, since multiple linear regression is nothing but an extension of the linear regression, we have learned how to conduct significance testing on individual regression coefficients. Alright, so if we have, let's say, 2 or 3 predictors, then predicting the effect of each of those predictors is what we do when we test significance on individual regression coefficients. Okay, and then we have learnt testing significance on a set of regression. Next we have learnt how to use the extra sum of squares technique to test for significance of a set of regression coefficients. Now let's say individual regression coefficients, it's okay. Let's say we have 4 coefficients. Alright, so we can test all 4 together. That would be testing significance of the regression model. We can test each of the 4 individually. That would be testing significance on individual regression coefficient. But what if we want to test for significance of, let's say, a subset of the 4, let's say 2 or 3, then what do we do? That problem is can be tackled well by the extra sum of squares technique. And last but not the least, we learned something about the confidence intervals and prediction intervals. Okay, so this was very briefly what we had learned during week 3 lectures, and I will give a little more intro and then we'll move on to solving problems. Okay, so the first question, as always, is how do we fit a multiple linear regression? So here again, how do we fit a multiple linear regression? The problem is to fit a multiple linear regression. What do we do? So let's say we have, since this is a multiple linear regression, let's say we have k minus 1 predictors. Okay, so then how will our model look like? Our model will look something like this. It will be y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta k minus 1 x k minus 1. Okay, note here we have k minus 1 predictors. Okay, but if we have to say parameters, then that would be k, because beta naught is also an unknown parameter. Alright, so be a little careful. K minus 1 is the number of predictors, and the total number of parameters including that intercept term will be k. Alright, now this one plus some error term, which will account for the variation which cannot be explained by these k minus 1 predictors. Okay, so here what we have to do is essentially the same thing. We just have to get the sum of squares of residuals. Okay, and then we have to differentiate it with each beta j and equate it to 0, and then by that process we would come up with how many equations? K normal equations. Okay, because we have k unknown parameters. So then we'll have k normal equations, and then we'll solve those simultaneously. And then we would obtain the estimates of beta naught hat, beta 1 hat, beta k minus 1 hat. Okay, the procedure remains exactly the same, but in order to facilitate this, we have introduced the matrix format. Okay, so if we do this entire calculation in the form of a matrix, we use the matrix notation, I would rather say, to do this. Alright, so we will have something like this. Ultimately, beta hat would be equal to x prime x inverse x prime y, where how do we write this? As the model will be written as y equal to x beta plus epsilon. Beta is a k cross 1 vector. We have to keep this in mind. Beta is not a k minus 1, it is k cross 1 vector, and x is a matrix which will be the model matrix, which would be of dimensions n cross k, and the matrix which would look something like this. So this will have 1, and then it would have the x1 values, then the x2 values. So it would be x11, x12, x13, so on to x1n. This would be x21, x22, x23 to x2n, and so on. Xk minus 1 column will be xk minus 1 1, xk minus 1 2, xk minus 1 3, and so on till xk minus 1 n. Alright, so this is how the model matrix will look like. And how will beta look like? Beta would be beta naught, beta 1, beta 2, beta 3 up to beta k minus 1. But dimensions would be k cross 1. Alright. So then what do? We have also seen that these properties which were holding in simple linear regression, those will also hold in case of multiple linear regression. So in case of simple linear regression, what did we see? We saw that expectation of beta hat or beta 1 hat, I would rather write it like this. So simple linear regression is a special case where k is equal to 2. Okay, we have something like beta naught plus beta 1 x1 plus epsilon, and we would estimate beta naught hat and beta 1 hat, and then we saw that they are unbiased estimators of their respective parameters, that is expectation of beta naught hat equal to beta naught and expectation of beta 1 hat was equal to beta 1. Similarly, we saw variance of beta 1 hat equal to sigma square by sxx, and variance of beta naught hat was sigma square 1 by n plus x bar square by sxx. Okay, what happens in case of a multiple linear regression? So the same thing holds for multiple linear regression as well. Here also we see that expectation of beta hat curl is equal to beta curl, and we see variance of beta hat is equal to sigma square x transpose x inverse. And if I want a very constituent elements variance, let's say I want beta p hat, then that would be sigma square x transpose x inverse that variables corresponding diagonal element. Okay. So first we have to get the inverse of this matrix, and let's say if I have something like this, I want beta 2 and I have beta naught, beta 1, beta 2, beta 3, let's say 4 parameters. Okay, so then this one would be a 4 cross 4 matrix. Then the third diagonal element of this inverted matrix would give me variance of beta 2 hat. Okay, fine. So then after learning these expectation and variance, we also learned some formulas. For example, how do we calculate SS residuals? SS residuals is nothing but this is y minus x beta hat transpose y minus x beta hat. So simplifying this, we get this as y transpose y minus beta hat transpose x transpose y. Okay, and we also see that degrees of freedom of SS residual is equal to n minus k. Okay, here we have to be mindful, k is number of parameters, or rather unknown parameters and not predictors. Okay, fine. So SS residual is this thing, and SST is y transpose y. Okay, and then SS due to regression, if somebody asks, then what will be the value? It would be y transpose y minus this. Okay, SST is not this. Sum of squares total variation is actually y minus y bar transpose y minus y bar. So that amounts to y transpose y minus n y bar square. This is due to regression would be this minus this. So you would land up at beta hat transpose x transpose y minus n y bar square. Okay, and the last day I was explaining, and I'm going to reiterate. So this thing SST equal to SS due to regression plus SS due to residual, this holds true everywhere. So this is total variation is divided into two orthogonal parts. The first one is going to take is the part which your regression takes care of. So this part of the total variance is explained by your regression, and this is the unexplained part. Okay, so then proportion of explained variation would be SS regression by SST, and proportion of unexplained variation would be SS residuals by SST. Alright, and another thing very important is the DF. So we know for SST, because of that constraint, that summation Wi equal to W bar, we always have one constraint. So this DF will always be n minus 1, number of individuals on which you have data, or number of entities minus 1. SS due to residuals will be n minus k, where k is the number of unknown parameters, and then SS regressions DF would be k minus 1. Alright, so these things we learned about how to fit a regression, multiple linear regression model. The next thing on our, so this is something which we have learned. Now the second thing is testing significance of regression model. So the second point was Alright, so what does this essentially test? This tests if there exists a linear relationship between the predictors and the response. Okay, so whether whatever predictor we have selected, they are actually useful in predicting the response or not. The H naught is defined in this manner: beta naught equal to beta 1 equal to beta k minus 1 equal to 0. Sorry, not beta naught, this is beta 1. Okay, so what I mean to say, if this is your, let's say, if this is your model, if each of beta 1, beta 2, beta k minus 1 is set to 0, then essentially you are not using any of the predictors. So what does it mean? That none of the predictors or this regression itself is not significant. Alright, now this is the null hypothesis. And what is the alternate hypothesis? The alternate hypothesis is anyone can be at least one of these coefficients can be non-zero. Okay, and how do we test for this? In order to test for this, we use or rather the F statistic. So how do we use this? We know that SS residuals by sigma square, this follows so this follows a chi-square n minus k, and SS regression by sigma square, this also follows a chi-square k minus 1, and these two are independent of each other. So by definition of an F statistic, we can write it as F equal to SS residual by sigma square by n minus k by SS regression by sigma square k minus 1. Okay, so then this cancels. This would be MS residuals by MS regression. Okay, and this one would follow an F k minus 1 n minus k distribution. Alright. So the test rule is such that the decision rule is we reject null H naught against H1 if and only if F observed is greater than F k minus 1 n minus k alpha, where what is this point correspond to? So if this is your F distribution, then this point here in green Okay, this one is your f k minus 1 n minus k alpha, such that the area above this point is actually alpha. Okay, and how do I check quickly whether a regression is significant or not? If we are provided with an ANOVA table, so that is also something that we have learned. So how does that ANOVA table look like? ANOVA table is analysis of variance. So first it will list out all your sources of variation. Okay, so in this case, in case of a multiple linear regression also, we have two sources. One is the regression and one is the residual. And then we would have something like the total source of variation. df, this would be k minus 1, this would be n minus k, this would be n minus 1. Sum of squares, we have learned how we can obtain it. This is sum of squares due to regression. This would be sum of squares due to residuals. This is SST, total sum of squares. And then we would have MS, that would be SS regression by k minus 1. And this would be SS residuals by n minus k. Okay, so this would be MS regression and this would be MS residuals. So the next column that we obtain, F, is actually the statistic which tests for significance of the regression line or regression equation. Okay, so F is MS regression by MS residual, and then F also follows an Fk minus 1 n minus k distribution, and we reject, and our rule is we reject H naught if and only if F observed is greater than Fk minus 1 n minus k alpha. Okay, fine. Apart from this, this is what we do when we want to find out how to test for significance of the regression model. Now, let us find out how do we do that when we test significance on individual regression coefficients. Okay, so what I mean to say is, I want to test, I have this plus beta k minus 1 x k minus 1 plus epsilon, and I want to test whether beta 2 equal to 0. Okay, versus h1 beta 2 not equal to 0. Alright, so in order to do that, we have known this equation, that beta hat equal to x prime x inverse x prime y, and variance of beta hat is nothing but sigma square x prime x inverse, and also variance of beta 2 hat would be sigma square x prime x inverse there that corresponding element. So if I take beta naught also, then this would be the third diagonal element. Alright, so following these, we also know that beta j hat would be would also follow a normal distribution, given that we assume that the errors are normally distributed, and since expectation and variance match, that would be beta 2, and this would be sigma square x prime x inverse 3/3th element, let's say. Okay, so once we have this distributional assumption, we can just formulate our own test statistic. So the test statistic is beta j hat minus beta j by root over sigma square hat x prime x inverse jj. Okay, and this one, if we would have had sigma square, it would have followed a normal 0 1, but since we have an estimate of sigma square, this will actually follow a t, and that would be the df of the SS due to residuals. This would follow a Tn minus k. Okay, and if we want to test if our h1 is this, that beta j is not equal to 0, then we should reject we should reject h naught if and only if this t if modulus of t observed is greater than Tn minus k alpha by 2. So what I mean to say is that if this is the t distribution which is symmetric across 0, this point is actually Tn minus k alpha by 2. So what does this mean? We will only reject t if this observed value is falling here, or if the observed value, this is minus Tn minus k alpha by 2, is falling below. Okay, so this is how we test for significance of each of the constituent predictors. Alright, now next comes the situation where we test significance on a set of regression coefficients. So according to the example that I was giving you, let's say we have something like this: y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, or some more, beta 4 x4 plus epsilon. Okay, so you can test all of them together. That would be your testing for the significance of the regression. You can test for individual parameters that would assess how suitable each of the predictors is in predicting your response variable. Alright, so now the objective is slightly different. Now if you want to check whether a subset, not one or all, something in between, let's say I want to test beta 2 equal to beta 3 equal to beta 4 equal to 0. So what I essentially want to say is that if I have to predict why x1 and x2 should be enough, these are extra coefficients which I don't need. Alright, so what do we do in those cases? There we use the extra sum of squares method. How do we do that? Step 1. First, we'll calculate the unrestricted SS due to regression and unrestricted S is due to residuals. Okay. And then step 2 would be to calculate restricted S is due to regression or restricted S is due to residuals. Alright, and then step 3 would be one of the following. Step 3 would be either option A, SS regression unrestricted minus SS regression restricted divided by R, okay, by R is the extra number of parameters, okay, by SS residual unrestricted by n minus k, and this would follow an FR n minus k distribution under H naught. Okay, if you write in terms of regression, that would be unrestricted minus restricted. If you are writing in terms of residuals, then we have to write SS residual restricted minus SS residual unrestricted by SS residual unrestricted divided by n minus k, and this should be also divided by R. This also follows under H naught FR n minus k. Okay, so this, if you just be mindful, if you are using regression, then unrestricted minus restricted, and if you are using residuals, then you would use restricted minus unrestricted. Okay, so the thing is simple, we have to keep the upper term positive. So I'll explain what I mean by restricted and unrestricted. So if I have y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Okay, so your H naught is, I think, beta 2 equal to beta 3 equal to 0. Let's say this is your H naught, and H1 is not H naught. Alright, so under unrestricted would be what? Unrestricted would be this entire model. Okay, so if I have to do it, then S is due to regression of this unrestricted model would be beta hat prime x prime y minus n y bar whole square. But what would be the dimensions of beta? Here beta would be how many? 1, 2, 3, 4. It would be 4 cross 1. X would also be n cross 4. Okay. And if I have to do sum of squares due to regression for the restricted model, then what do I mean by restriction? We mean and imposing H naught. Okay, imposing H naught. So if you impose H naught, 2 and 3 will become 0. So then we'll have a simple linear regression. So SS due to regression will, that in that sense, would be beta star x prime y minus n y prime y bar square. So in this case, this will be x star. So in this case, beta star would take dimension 2 cross 1. Okay, and x will also be n cross 2. Okay, and when I am using regression, then I should use unrestricted minus restricted, because unrestricted will have more variables, it will explain more variation. Okay, but restricted will have less variables, it will explain less variations. But on the other hand, if we just flip it around, if we are using SS due to residuals, then for this full model the residual will be less, but for a restricted model the residual would be more. So if I have to make that difference positive, I should keep SS residuals restricted minus SS residuals unrestricted. Okay, both the formats are equivalent because SS total cancels each other out. Alright, so once we have this, either the SS due to regression or SS due to residual, restricted minus unrestricted, that thing is taken care of, then these ratios follow an FR comma n minus k distribution. Okay, and the other thing is it follows this distribution, and the most important thing is decision rule. So what will the decision rule be? Decision rule would be to reject H naught if and only if F observed exceeds F how much would this be? This would be FR and this would be n minus k. Alright, now once this is done, the last thing that we discussed was confidence intervals and prediction intervals. Okay, so for confidence intervals, what did we do? So the trick is to keep the unknown parameter in the middle and then get bounds on its right and left side, such that probability that this variable lies within the specified bounds is equal to the amount of confidence that you require. Okay, so just to touch up briefly, we know that beta hat is x prime x inverse x prime y. Okay, and variance of beta hat we have seen it would be sigma square x prime x inverse. Okay, and each beta j hat follows a normal beta j with sigma square x prime x inverse that matrix jth triangular element, sorry, jth diagonal element. Okay, now for individual level of testing, what did we do? We found out we had this test statistic that beta j hat minus beta j by ms residuals x prime x inverse jj root. This would follow a t, how many degrees of freedoms of the residuals, so n minus k distribution. Okay, so this would hold. Now what do I have to do? I have to use this equation to devise bounds such that probability this bj lies within those bounds is equal to 90% or 95%. Okay, so what essentially I have to do is that I have to find out So I have to exploit this equation. So I can write it as probability beta j hat minus beta j by root over ms residuals x prime x inverse jj. This lies between t n minus k alpha by 2 and minus t n minus k alpha by 2. This probability is equal to 1 minus alpha. I can write this. Why? Because if this is my t distribution symmetric across 0, this point here, this is t n minus k alpha by 2 means the above area is alpha, and similarly minus t n minus k alpha by 2 means that the below area is alpha by 2. This is also alpha by 2. So if this thing which follows this distribution falls within these two bounds, then that probability will be this unshaded area, that is 1 minus alpha. So once we have that, the only goal is to keep beta j in the center and then adjust accordingly. So what will we have it as? We will have it as P beta j hat minus t n minus k alpha by 2 root over ms residual ms residual x prime x inverse jjth element less than equal to beta j less than equal to beta j hat plus t n minus k alpha by 2 root over ms residual x transpose x inverse jjth element. This entire thing is 1 minus alpha. So then this one, so then 1 minus alpha percent ci would be beta j hat plus minus t n minus k alpha by 2 root over ms residual x prime x inverse jjth element. Okay. And apart from this, we also learnt confidence interval of mean response at a particular point. Okay. So what does that mean? It means that given x, what can be an estimate of the expected value of y. All right. So the first thing that they've given is, given this is confidence interval on mean response at a particular point. Okay. So now let's say that point x is given as 1, x naught 1, x naught 2, x naught n. Okay. So then expectation of y given x naught would be x naught, or it would be rather x beta. Okay. Now an unbiased estimator would be expectation of this would be beta hat. Because why? If we give expectation of y given x naught hat, then this would be expectation of x transpose beta hat, it would be x transpose beta. Okay, so this is an unbiased estimator of this quantity. All right, this is nothing but y hat. All right, so from here we get y hat is an unbiased estimator of y. All right, and now we are going to find out what? We are going to find out variance of y hat. Okay, so then that would be variance of x transpose beta hat. Okay, so this would be x naught, sorry, not here, I should give x naught for parity. All right, so this would be x naught prime, sorry, this would be x naught variance of beta hat x naught prime. Sorry, this would be x naught prime variance of beta naught into x naught, because this is 1 cross p. Yes, done. All right, so now this would be x naught prime sigma square x prime x inverse x naught. All right, now we have this and we also have this. Then y hat is actually a linear combination of normally distributed variables, so it would also follow a normal distribution. So we would have something like this, that y naught hat follows, excuse me, sorry ma'am, I cannot hear you. Hello? Is there any specific question that you have? All right. So then this would be y naught hat would follow a normal distribution with y naught and this as its variance, sigma square x prime x inverse x naught. Okay, and then we can write that y naught hat minus y naught by root over sigma square x transpose x inverse x naught. This follows a normal 0 1. Okay, and this would be x naught transpose beta hat minus x naught transpose beta divided by root over, if we replace sigma square by ms residual, x naught prime x prime x inverse x naught, then this would follow a t n minus k distribution. Alright, so the prediction that we want is this quantity. So in order to do that, what we need to do is keep this in center. So then we can write it like this: P x naught transpose beta hat minus x naught transpose beta by ms residual root over into x naught prime x inverse x naught lying between t n minus k alpha by 2 and minus t n minus k alpha by 2. This would be 1 minus alpha. So therefore 1 minus alpha confidence Ci for mean response at x naught would be Ci for x naught prime beta, which would be x naught prime beta hat plus minus t n minus k alpha by 2 root over ms residual x naught prime x inverse x naught. Alright, fine. So now that we have discussed these problems and not exactly problems, we have discussed these formulas, let us now solve a few sums so that we know how to use all of these. Okay, 1. Here what is it saying? It says weight is regressed on height of 40 adults. The height range in the data is estimated as 50 to 100 and the regression line is this, with r square equal to 0.12. So the question is, which of the following conclusions doesn't necessarily follow? So then, what does this say? The adult with an x value of 60 has an estimated y value of 106. X value of 80 has an estimated y value of 108, or this one, adult with an x value of 90 has an estimated value of 108. So if we plug in x equal to 60, we get 106. If we plug in x equal to 108, then we get, x equal to 80, then we get 108. If we plug in x equal to 90, this is 109. So all of these are true. But this one, conclusions does not necessarily follow. The data suggests weak relationship between x and y. This may or may not be true. Why? Because r square 0.12, whatever is given over here, is suggestive of a linear relationship. It may very well be possible that x and y could have some other form, maybe some quadratic relationship or some cubic relationship may exist between x and y. Okay, so since they've not mentioned here linear, this doesn't necessarily follow. Okay, and this r square also sort of depends context wise. In some applications, maybe r square greater than 80 could be my cutoff, but in some applications maybe r square greater than 60 is good enough. Alright, so based on these observations, we can say that option A doesn't necessarily follow. Okay, because these three holds. Y equal to 100 plus 0.1x, so x equal to 80 would mean 100 plus 8, 108. Okay, so these three holds and A is not necessarily true. Moving on. Question 2 says, when we add a new regressor variable to a multiple linear regression model like this one, which has, so this model has k minus 1 predictors and k parameters. Okay. Now we are adding a new regressor variable. So the value of r square cannot go down, because what r square is measuring SS due to regression by SS due to total. Okay, so SST equal to SS rig plus SS residuals. Now this part is actually explained by your y equal to beta naught plus beta 1 x1 plus beta k minus 1 xk minus 1, and the residual is this part. So if we add more here, the residual part will become less and this will become more. So r square will automatically increase as we keep on adding variables. Okay, that's why I was saying r square is not a good measure for detecting the number of parameters a model should have. Instead, we should use adjusted r square, because that takes care of the trade-off between the increase or rather decrease in the errors residual sum of squares and the cost of including another variable to the model. Alright, so r square, as we keep on adding variables, r square value will keep on increasing and it cannot go down. Fine, let's move on to the third one. Here it says that this studios operates portrait studio in 21 cities of medium size. Okay, the studios specialize in portraits of children. Company is considering an expansion where sales is predicted from number of persons aged 16 or younger, because they are children. So this is the target population I have, and the per capita disposable income in the community, which is x2. Okay, so then x1 is the target population and x2 is the per capita income. And this is the data on 21 cities. So n would be 21. Okay, so we had something like this, a model matrix 1 1 1 1 x1 target population data and x2 those data, and from that we have constructed this x prime x matrix, and this is the x prime y vector. Alright, so what is the least square estimate of beta naught? So how can we do it? First we'll get beta hat, that would be x prime x inverse x prime y. Okay, so then we have to compute this inverse of this matrix. Alright, so how do we do that? So x prime x inverse would be adjoint of this x prime x and then divided by determinant of x prime x. Okay, so finally we will have something like this. X prime x inverse would be 29.574023. This would be 0.717,588. This would be minus 1.981973. This would be 0.0003689. This would be minus 0.0055207. And this would be 0.13558,763. So this would be the value of x prime x inverse. Now if we calculate this beta hat, then it would be this x prime x inverse into x prime y. Okay, and beta naught hat would be first row multiplied by first column. Okay, so it would be 29.574023 into x prime y was how much? 3820 plus 0.0717588 into this value 249643 plus minus 1.9819703 into this thing 66073. So if we calculate, this value will come close to minus 68.857. Okay, this would be the least square estimate of beta naught. Now moving on, what is the least square estimate of beta 1? So same thing, beta 1 hat will be second row into second column. Now this is actually a symmetric matrix. So here we would have 0.0717588. Here we would have minus 1.9819703. Here we would have minus 0.0055207. Okay, so second row multiplied by second column would give me how much? Would give me beta 1. Okay, so then this is 0.0717588 into this value 3820 plus 0.0003689, 0.0003689 into how much was this? 249643 plus again this one, this element minus 0.0055207 minus 0.0055207 into the last element of x prime y, that is 66073. 66073. So if we calculate, beta 1 hat will come very close to 1.455. Okay. And similarly, if we want to calculate beta 2, we'll have to do this third row into column. So that would be beta 2 hat would be this thing, minus 1.98 into 3820 plus minus 0.0055207 minus 0.00020 55207 into that large number 249643 249643 plus again 0.13558763 0.13558763 into this thing 66073. So if we calculate, this will come close to 9.366. Alright, fine. Now that we have this, let's move on to the next question. This question says we have to calculate SS due to residuals. Now SS due to residuals would be how much? This is actually y transpose y minus beta hat transpose x transpose y. Okay, so now here what do we have? Beta hat is beta naught hat, beta 1 hat, beta 2 hat. So this is actually minus 68.857, 1.455 and 9.366. Okay, so then y transpose y is how much? Y transpose y is given here. This is 7210, 72.40. So this is 7210 72.40. Y transpose y is given. Now beta hat transpose x transpose y is minus 68.857, 1.455, 9.366 into 3820, 249, 643, 66073. So if we calculate this would be how much? So this amounts to 719036.543. So therefore SS due to residuals would be 721072.40 minus 719036.543. So this would be something 2035.857. Okay. Maybe I've done some mistake in calculation here. Alright. So whatever it is, the procedure is this. Y transpose Y we'll have like this. Beta hat transpose X transpose Y we have to calculate and then find out the sum of squares due to residuals. Okay. Now the next thing is consider the problem how to find out sum of squares due to regression. Okay. So for that we have to find out SST minus SS residual. Now SS residual is already given, or rather SS due to regression we can also find out by this formula, beta hat transpose X transpose Y minus n Y bar square. Okay, here we wrote it. N Y bar square. So since we already have this is something amounts to what? We calculated in the previous one 36.543 minus 21 into Y bar whole square. Now what is Y bar? Y bar is given here. So summation yi is 3820. So Y bar will be how much? Summation yi equal to 3820. Y bar will be 1 by 21 summation yi. Okay. So this would be 21 into Y bar square. So it would be 3820 by 21 whole square. So this would be 719036.543 minus 21 into minus 3820 square by 21. How much does this come to? So this amounts to 24160.35. Okay. All right. Maybe some calculation mistake is happening, that's why these figures are not matching, but you get the idea. This is the formula that we have to use. All right. Okay. Now the question is, what is the degree of freedom SS residual? SS residual degree of freedom is n minus k, where k is the number of parameters. Okay. So here we have what? Y equal to beta naught plus beta 1 x1 plus beta 2 x2, where beta 1 corresponds to effect of that target population and beta 2 is the effect of per capita income. So in this case, k is equal to 3. Okay. So SS residual's degrees of freedom would be 21 minus 3, that is 18. Similarly here, what is the degree of freedom of SS due to regression? That would be k minus 1. So here k is 3, therefore SS regression df would be 2. Alright. Now consider the data. Approximately what proportion of variability in y remains unexplained? So proportion of variability remaining unexplained is actually SS due to residual by SST. Okay. So it would be, how much was our SS due to residual? Was something around 2035.857. So this is 2035.857 by SST was how much? 72, that number, that big number, 7210, 72.40, 7210, 72.40, and that is the proportion which is left unexplained. 2035.857 divided by 7210, 72.40, this into 100. So this is 0.28%. Alright, moving on. This is how much of the variation in y about y bar is explained by x1 and x2. This is essentially SS due to regression by SS total, or in other words R square. Okay, so we'll just find it out, how much is explained, what percentage. So this would be 24160.35, 24160.35 by 721072.40. So that would be 24160.35 plus 721072.40. This one divided by that one. Okay, so that is 3.3%. Somewhere there is some problem has happened, because these proportions should add up to 1. Okay, so something is off here. We just have to check the calculations. Or no, this is fine. The problem is SST is this one minus ny bar square. Yeah, got it. So this would be SST is actually y transpose y minus ny bar square. So this would be 721072.40 minus 3860 whole square by 21 into. So this would be 721072.40 minus 3860 square by 21. 3860 so this would be 721072.40 minus 709504.7619. Okay, so 721072.40 minus this is actually 11567.6381. so this one would be SS residuals would be 2025.857 divided by 11567.6381. So that is 2025.857 divided by 11567.6381. So this would be 17% approximately. Okay, and this will be this will make up for the remaining 100 minus 17%. So it would take up 83%. Alright. Okay, this is not 3860, this is 3820. Oh, some mess up. Okay, this is 3820. Yeah. So this would be 3820 square. So this value changes to 3820 into 3820 divided by 21, 721,072.40 minus this thing. This actually is total sum of squares is actually 26196.209. Okay, so this would be proportion of unexplained would be SS residuals by SST. This is 26196.209, and that would be 2025.857 divided by 26196.209 into 100. So this is actually 7.7%, and this should typically come to 93% or something above 92.7. This should be greater than 92.7%. So that should be your check. So SS due to regression is how much? That we have found now, 24160.35. It would be 24160.35 by, this is 2416 divided by SST. SST is how much? 26196.209. 26196.209. So this is 2124160.35 divided by 26196.209. Yeah, so this comes to 0.92.22, so approximately 92.2%. Okay, some approximations error here and there might have happened. All right. So 92.3 plus 7.7 should amount to 100%. All right. Fine. Now the next question is, consider the data in problem 3. Is the fitted model statistically significant? So we have SS residuals, we have SS regression. Okay, to test for this H1, to test whether the model is statistically significant, we need to test for this one, H0, both beta 1 and beta 2 equal to 0. Okay, and which is equivalent to testing H0 R square equal to 0. Alright, now how do we do this? We want to test beta 1 equal to beta 2 equal to 0. So we know SS residuals, we know SS regression, we know DF residual, we know DF regression. Okay, so first I'll just write it down. So SS residuals is how much? We calculated 2025.856. So this is 2025.8567. And SS regression is how much? SS regression also we calculated. This was 24160.35. 24160.35. DF residuals is n minus 3. So that is 21 minus 3, that is 18. DF regression is k minus 1. So that is k is 3. So here this is 2. Okay. So then the F statistic is what? MS regression by MS residual. So this is what? This is 24160.35 by how much? It would be k minus 1. So 2 by 2025.857 by 18. Alright, so how much does this come to? This would be 24160.35 into 9 by 2025.857. So that would be 24160.35 into 9 divided by 2025.857. So this value is something close to 107.33. Okay, and we have to find out the F statistic corresponding to this thing. So what would be that DF? That would be F k minus 1 n minus k alpha. So at 5% level of significance, if we want it, then it should be a F218 0.05. So that should be that point such that this area above is 0.05. This point we need. Okay. So we can calculate it from a table or we can get it from elsewhere as well. So let me just find out. Okay, so here is the F table critical value. Yeah. Okay, so for DF equal to 218, DF1 2 and DF2 would be 18. So this is the critical value 3.55. So this thing is 3.55. Okay, and our F observed is 107. .33, which is greater than the F critical. Therefore, we reject H naught and conclude. What will be the conclusion? H naught says that x1 and x2 have no effect, but we are rejecting H naught and we conclude that yes, they have effect. So the regression is significant. Alright, so we are actually rejecting the null hypothesis. fine. Now if we go here, if we have to test whether cells are related to target population or not, we test for beta 1 equal to 0. So then what will be my test statistic? My test statistic would be beta 1 hat by root over ms residual into x prime x inverse 1/1th element. So in this case, if this is my x prime x inverse, then this is actually, this corresponds to beta naught. So if I'll just copy this table here. So here you see this one corresponds to beta naught, this one corresponds to beta 1, and this one, this element over here corresponds to beta 2. So for this thing we'll have ms residual x prime x inverse 1/1th element, or rather 2/2th element. So this we'll have this one 0.000036899, 0.000036899. okay, and this under h naught would follow a t n minus k distribution. Okay, and we would reject h naught if and only if t observed, mod t observed is greater than Tn minus k alpha by 2. Okay, so let us find out what will be this thing. So beta 1 hat value we have obtained, ms residual we have obtained. So let us find out how much it will be. So t observed is, beta 1 hat was how much? We had obtained it earlier. Beta 1 hat was 1.455. So this would be 1.455 divided by root over ms residual was how much? We calculated 2025.857 by 18. 2025.857 by 18 into 0.00, what was that? 0.36899. So let us calculate 1.455 divided by square root of 2025.857 into 0.00036,899 divided by 18. So this entire thing is something close to 7.14. Okay, now we have to find out t n minus k, that is 18 alpha by 2, that is t 18 0.025. Alright, so to do that we need the t table. Okay, so here we have our t table. We want this one tail t 0.025. okay, this thing, so that two tailed will be 0.05, and our df is 18. So what we need is this value 2.101. okay, so t critical in our case is 2.101, and we find that our t observed modulus is greater than t critical. Therefore we reject h naught and conclude that x1 or target population is significant. Alright, so similarly for this thing, what do? Beta 2 not equal to 0, same thing, the t observed will be beta 2 hat by root over ms residual, and this would be x prime x inverse their third diagonal element. So here it would be ms residual into this one, 0.13558763, 0.13558763. Okay, so this one will be 9 point whatever was its value, 9.366 divided by root over 20, what was this, 2025.857 by 18 into 0.13558763. So if we calculate 2025.857 into 0.13558763 divided by 18, then square root of that, square root of this thing, and 9.366 divided by this value. So this comes to something around 2.39. okay, but here again this one was 2.101. okay, here also our t n minus 18 0.025 is 2.101, right, from the table. Yes, so here also we see t observed modulus is greater than t critical, hence we reject H naught. Okay, we reject the null hypothesis and we conclude that per capita income is significant. Alright, now if during the exams you are, instead of providing with the values, you are provided with this thing, you are asked to find estimates, all you need to do is find the matrix notation for this. So y would be this thing, 66.0, 43.0, 7.6. Your x matrix will be, if you have a beta naught term over here, then you will have all ones over here. Then your x1 term will come 38, 41, 32, 47.5, 21.3, so on and so forth. But note, if you are asked to find a fitter linear regression without intercept, like beta 1 x1 plus beta 2 x2 plus epsilon, in that case your x model will not have the 1 coefficients, it will only directly have your x1, that is 38, 41, so on, 47.5 to 10, and in that case your beta star will only have beta 1 and beta 2. In this case, your beta will have beta naught, beta 1 and beta 2. Okay, so be very careful how you are formulating this, and the formula remains the same, so you would be able to calculate it. That won't be an issue. All right. So that was all for today. If you have any more questions, please let me know. Alright, if nothing, then I'm going to see you in the next class. Meanwhile, if there are any questions, please post it in the discussion forum. Thank you so much for joining.